Hello, over the last several videos we've been introducing different techniques of integration. We've looked at substitution, we've looked at integration by parts, we've looked at how to use certain algebraic techniques and trig identities to help us, including long division, partial fraction decomposition, and some other techniques. But mathematicians over the years have developed many integration formulas, and they've collected them into tables, and one can purchase large books of such formulas. Using them is not quite as straightforward as just saying that they're in a table might suggest. They usually require the user to make at least some substitutions and still make use of some skills from pre-calculus, such as the ones we've been using in our integrals so far. And most introductory calculus texts have tables of integrals in the appendices. The current textbook that we're using as of this video has 100 such formulas in Appendix B. But I will say today it's much more common to use a computer algebra system to work out difficult integration problems. And the programmers of these CAS programs made use of the known integration tables. We've seen how we can check derivatives, antiderivatives, and definite integral calculations using a TI-84 calculator. We've also seen how to use technologies such as GeoGebra or TI-inspired CAS to compute formulas for derivatives and antiderivatives and to find exact values of definite integrals. And there are also free GeoGebra apps for your smartphone, so this technology can easily be with you always. And there are also other internet-based applications that will do these computations as well. For example, Wolfram Alpha is a good source for an internet-based program for doing all sorts of mathematics. You may not even need to type in anything. You can probably just verbally ask the digital assistant on your phone to find an integral for you. Try this one out. Hey Siri, what is the integral of sine squared of x times cosine cubed of x?
One moment. I found an answer. It's displayed on your iPhone.
So that thing on my iPhone took me to Wolfram Alpha, and there's a page here that shows the indefinite integral. There's a plot. It's a periodic function, so there's a plot of it with one period going either side of the origin, which it does go through, and then another one with more periods. Then there's some alternate forms placed in a couple different forms, maybe using some different trig identities, and so forth. So it gives series expansions, some things that we'll talk about a little bit later in the semester. So, lots of stuff, a lot more than you would get just by actually doing it by hand, comes out right there just by, you don't even have to type in anything. So it's pretty amazing the technology that's available now. And of course, with this level of technology readily available to us at all times, it is true that the skill of finding these antiderivatives and definite integrals is really not the most important part of calculus. Nevertheless, you should become proficient in these techniques and these notes in order to gain skill in working with formulas and working through sometimes lengthy processes. Those are still useful things for us to do. And of course, I will be, because of the use of the technology, I'll be requiring no technology for our class exam on this material. I'm not going to say a whole lot more about integration by tables, but there is a section in your textbook that you should look at that I think will cover that well. Now let's talk a little bit about numerical integration. I've actually talked about this quite a bit earlier. So I consider understanding approximation methods for definite integrals to be a critical part of understanding of the meaning of the definite integral. So I introduced left, right, and midpoint Riemann sums and the trapezoidal and Simpsons rule approximations of integrals in Calculus 1. And at this point, you should go back and read or reread my notes and or rewatch videos on Unit 3, Definite Integral, Concepts, Definitions, and Approximations. In particular, of my notes, study pages 24 to 48, where we go through a careful development of these numerical integration techniques. So in those notes, I use the following definitions. Okay, delta x, the change in x, from one end of the interval from a to b, is b minus a over n, where we're dividing this up into equal sub-intervals. So we're trying to approximate this integral from a to b of f of x dx. We divide the interval up from a to b up into equal spaced and equal width intervals, sub-intervals of length delta x, which is b minus a over n. Then write Riemann sum within sub-intervals, sub-rectangles, is we go to the right end of each interval, sub-interval, and that would be at a plus k delta x. Then we do f of that to grab its corresponding output, y value, multiply by this common width, and sum that up, and that gives us a right Riemann sum. Similarly, the left Riemann sum, we go to the left end of each interval, which is 1 delta x back from the right end, so that's a plus k minus 1 delta x's. We don't want that x, we want the y that goes with that x, so you do f of that. Then they'll give you the signed height of your rectangle, then multiply by this width, delta x, and then add that up. The trapezoid rule estimate is just the average of the left and right estimates, and we saw how we could see that both as a series of rectangles, areas added up. The rectangles are halfway in between the left and right rectangles in terms of their heights, but we also saw how we could see that as the area of trapezoids, where the top of the trapezoid is a little secant line segment from one end of the from the function to points on the function from the left end of the interval to the right end. The midpoint rule takes the x value in your interval to be exactly in the midpoint horizontally on your input interval. So that's a plus k minus a half delta x. So it's half of a delta x back from the right end. Okay, take the y there, f of x, f of that, multiply by the width, and sum it up. And so we can easily see that as a Riemann sum, and that is a sum of rectangular areas. But we also saw we could see that as a sum of right trapezoids as well. This time the top of the trapezoid is a tangent line segment that is tangent to the point above the midpoint of that interval. Simpsons rule then is a weighted average of the trapezoid and midpoint. The midpoint rule is typically about twice as good as the trapezoid rule. And so we take two midpoints plus one trapezoid divided by 3, and this is typically called Simpsons of 2n when you use n here. So you use trapezoid 3 and midpoint 3 to find Simpsons 6. Okay, and then you can actually take the limit of any of these guys as n goes to infinity, and it will go to the definite integral. We took the right Riemann sum one and used it as our definition. Okay, when you apply the limit, of course, as n goes to infinity. And of course, notice you also have to make sure these delta x's go to 0, but by setting them up as equal widths, that's what we get. Now, there's a more general definition of this where we don't have to let the widths go to 0. We don't always have to go to the right end of each interval, but this gets you what we need. Now, I will point out that if you look in your textbook, you may see what looks like different formulas for the trapezoid and the Simpsons rule, but those are actually totally equivalent to the way I've got it here. And to me, this way makes more sense, and it also is a way to you can get all of these different estimates when you're working towards Simpsons rule, and you're basically refining your estimate more and more and more. Okay, but if you want to use the formula that's in your text, then that's certainly fine. It's the same thing. So that gives us some approximation techniques. So let's put those in work in an example here. So let's just see if you can try this one. Approximate the integral from 1 to 10 of e to the minus x squared dx using left 3, right 3, trapezoid 3, midpoint 3, and Simpsons 6 estimates, and give all the decimal places provided by your calculator. I want to point out that this is an example of a relatively simple looking function that in fact has no antiderivative built up out of elementary functions. In other words, if you put together any combination of add, subtract, multiply, divide, powers, roots, exponentials, logarithms, trig functions, inverse trig functions, hyperbolic trig functions, none of that can build out an antiderivative of this particular one. So we really have no choice but to use some approximation technique on this. So this idea that when you have something built out of elementary functions, we can find the derivative of any of those functions, just given enough time and patience using our basic derivative rules. But reversing the idea of taking a function and finding an antiderivative is a lot more subtle. Sometimes it's quite easy, but sometimes it can be very difficult, and then sometimes it can even be impossible, like on this one. So let's proceed on with this. See if you can find these estimates, and we'll check your work here in just a second. Press pause now. Okay, hopefully you've done this yourself. So here are the estimates. Okay, so A is 1, B is 10, so B minus A is 9. Our interval has length 9, and we're going to divide it into n equals 3 equal intervals. That gives us a delta x of 3. So the first interval goes from 1 to 4, the next one goes from 4 to 7, and the last one goes from 7 to 10. So left Riemann sum, our left sides are always at 1, 4, and 7. Okay, and you evaluate the function at those points, e to the negative 1 square, e to the negative 4 square, e to the opposite of 7 square. By the way, notice that you square first, then you take the opposite when you're doing that. So we're not squaring negative 1, we're squaring 1 and then taking the opposite. So this first one, this is e to the negative 1, that's e to the negative 16, e to the negative 49. Use your calculator to approximate those and multiply by the common width of 3. Since it's a common width, I can factor it out front. And I get approximately 1.1036, etc. You can see it here. The right Riemann sum, basically these two terms are going to be the same because the left end of the second interval is the right end of the first one. So the right end of each interval is 4, 7, and 10. Plug those in and evaluate again, multiplying by 3, and we get a much smaller amount here. 1, 2, 3, 4, 5, looks like 6 zeros, and then a 337,606. The trapezoid rule is just the average of the right and left, so we add those two numbers together and divide by 2 to get about 0.55. The midpoint rule is, well, we want to go halfway in the middle. So halfway between 1 and 4 is, well, add 1 plus 4 divided by 2, that's 5 halves, or 2.5. Halfway between 4 and 7 would be 11 halves, or 5.5. And halfway between 7 and 10 would be half of 17, which is 8.5. And so we evaluate the function at those points, 2.5, 5.5, 8.5. Work that out on your calculator, multiply by 3, and we get this for the midpoint rule, 0.00579, and etc. To get Simpsons rule, notice it's Simpsons 6, not Simpsons 3, even though it uses the 3's here, is we average the trapezoid and midpoint, but we count the midpoint twice. So it's the trapezoid rule here, plus 2 times this midpoint, divided by 3, you get 0.187800741,394. Okay, and you will find some more about these approximations in your textbook as you read that. Just a couple things. The left and right Riemann sums are approximating the function with a horizontal line. Trapezoid and midpoint are approximating with linear functions. So left and right are constant functions, trapezoid and midpoint are linear, where in different ways. The trapezoid rule approximates the function on each piece with a secant line segment from both ends. The midpoint rule approximates with a linear function, which is a tangent line segment in the middle of the interval. And Simpsons rule actually approximates with quadratic functions with parabolas hitting at the middle of the interval and at both ends of the interval, hitting at those 3 points. And Simpsons rule is actually quite good. Again, I'll refer you back to my earlier notes for some more details on this. Let me just continue on for just a minute here. I have, following this, more integration problems. I'm not going to go over all of these at this point in the video, but I am going to run through a bunch of them real fast. If you want to stop the video and look over the work, you can. But there are a variety of different ones for practice here. And some of these I'll check. I'm not going to comment on these at the moment. I'm just going to kind of go through here kind of slowly. And where you can pause the video if you need to for some more practice and more examples. And for students in my class, you'll have these actual notes, so you can look at the notes and use them to practice a little bit more. Hopefully at this point you'll be able to at least follow what's going on with the steps all worked out in detail. But there are many more examples practicing the various things that we're going through here. Here's a rational one, long division, partial fractions. This one here is just a straight substitution, but it is an indefinite integral. I introduced indefinite integrals in my Calculus 1 notes, so go back to that if you need to. And there is there's a pretty basic one there. And then this one here is a straight substitution. This one is straight substitution. There's another one. So some of these are just straight substitution problems. They're kind of mixed in. Some of them use trig identities. It uses a trig identity. There's a rational function, so it's going to use a long division there. And some partial fraction, decomposition there. Continuing the partial fraction decomposition. And then once you have that, you can work out the integral. Here is here's one that we're going to do by parts. Here's one here. It's also by parts using the table method. Looks like we got a trig substitution. Trig substitution coming up here. I need to clean up my picture there to show the sides. Let you figure that out. This one is just a basic substitution, except you got to be careful on this one because there's a discontinuity in the middle of the interval. See, it's undefined when x is 1. So we have to break this into 2 intervals. And we see actually this one is undefined. It diverges. Here's one here, another improper integral, because we have the infinity here. And then at the end here, it's time to go and finish some homework. Okay, finish up all the homework that I have for the unit, and to study the rest of the textbook for that unit. And then I have some review exercises. So there's a handful of exercises here. I think this may have been an exam I gave in a pass, so that's a good study for exams. So here are 8 problems that you might try on your own. Okay, and then here are the solutions to those. There's one. There's a solution to 2, which is a trig identity one. This one is a integration by parts table method. Check. All right, here we see one where we just do a trig substitution. And here's a rational function one. So it looks like some long division and probably some partial fraction decomposition done down here. Here's factoring and partial fraction decomposition on the side. Then you can pull it back up here to the top and finish it. Check. This is an improper integral. And it's actually solving an equation, figuring out what the c is going to be. This kind of thing might be used in the probability theory a lot here. Something like that. Here's another example where you're finding a specific antiderivative. So here we find the family of antiderivatives, substitute the constant, find the specific one. And it looks like we got another trig substitution. Okay, and then it's time to be prepared for your exam at that point. So hopefully you'll find those helpful to you. Happy integrating.